Okay, so today's notes are an average value of a function. I want to take a second before you really go anywhere, and you can write in this area if you'd like, to kind of think about a few things. The first thing I want you to understand is, if you take the area of like a shape, let's say a simple rectangle, okay? Well, how do you get the area of that? Isn't it base times height? Base times height. Or width times height, right? If you want to call that base, you can call it base. If you want to call it width, you can call it width. So if you just multiply the width times the height, you will have the area. So let's just write that out for a moment. So area equals width times height. Well, if you think about it, and you want to know the average height, you want to know the height of something, how would you solve this for height? Well, you divide by width. So if you took the area of something and you divided it by its width, you'd have the height. So what we're going to do is we're going to take the area of a region and we're going to divide it by the width of that region, and that's going to give us the average height of that region. You might not understand it until you see it, but I think seeing it will really lock it in. So, average value of a function. So if I say I need to find the average velocity, okay, if I need to say I need to find the average temperature, if I say I need to find the average, I don't know, average number of bananas, okay? I know it seems like a weird one, but it was an AP question recently. If you need to find the average of anything, you're going to find the average value of that function. How do you do that? Well, if you can integrate something from A to B, if you can integrate it, if it's possible, then the average value of that function is going to be this right here. And let me explain a little bit more about what this means. So first of all, what this means is you got a graph, okay? And let's say you're trying to, I don't know, you're trying to figure out the average height of this right here. From here A to here B, okay? And if you look at all these heights in here, you see like, okay, well let's call this 2, and let's call this 4, okay? And you might say, okay, well the average height in here is probably around 3. Maybe it's a little bit lower, a little bit higher, but it's probably somewhere around here. Okay, maybe it's a little higher than that. But you know, that's basically what we're trying to find. We're trying to find out what is a height that kind of averages this out. So if you look at that, and you kind of look at this for a second, you say, well look, here we didn't get this part, but this part we did get. And do those kind of cancel each other out more or less? Yeah. So what you could say is like, yeah, the function was at 2 and then the function was at 4, but on average it was right around 3. The only way you're going to be able to do that is if you can take the area under the curve and divide it by the width. So you need to take this area right here, area, and you need to divide it by the width, which is going to be this right here. So let's just kind of build that for a second. Well, what is the area under the curve from A to B? The area under the curve from A to B is the integral of the function from A to B. What is the width of this region? How do we find out what it is from A to B? We don't know what A and B are, but let's say A was 3 and B was 7. Well, what's the width? 4? Let's say A was -1 and B was 6. What's the width? 7, right? You don't have to write all this, but you get an idea. What you're doing is you're subtracting B minus A. So your width is simply B minus A. So what I want you to kind of do for just a second is to understand how this becomes this. So I want to see how these are equal. Area under the curve right here from A to B. So that's the area, that's the purple part. And then we have to divide by the width, which if you just subtract those numbers, you'll get the width. So that's that. So now you can hopefully understand where that's coming from. And now what I want you to do for just a moment is I want you to kind of understand how this is this. Right? These are the same. Samesies. And I mean, the calculus texts always like to write it like this. So does the AP exam. That's how people like to think of it. But conceptually, this makes a lot more sense. So I'm going to try to push this because it makes more sense to think about area divided by width being height. And this is going to give us that average height. So remember, if you're looking at a graph, we're trying to find the average height for that time, for that interval, over that spot. And this is different than average rate of change, but they are connected in a way. I don't want to really make it too intense, so I'm not going to talk about average rate of change and how they're connected, but they are connected. But it's different than average rate of change. So watch out for this word average. Okay, let's do an example. So how do we do it? Well, what we need to do is we need to find the area under the curve, which I will do in red. So I'm going to do the area divided by, and then we need the width of the region. That's really what we need. So I'm going to put a giant fraction line there, and I'm going to try to figure out the area under the curve. So what is the area under the curve? Well, that's just the integral from 1 to 4 of 3x squared minus 2x dx, right? Minus 2x dx. That's really what it is. Technically, there should be parentheses here all the time, but we are not going to be great about that. Now we need to know the width of the region. Well, it's from 1 to 4. So really what you need to do is you need to do b minus a. But we know in our heads that that's just 3. So we have to take that whole entire integral and then divide it by 3. What would the book have said? The book would have said 1 over b minus a. And then the integral from 1 to 4. 3x squared minus 2x dx. Okay, we don't need this. We're going to do it our way. It's going to get the same answer. All it's doing is making it into a little bit complicated of a fraction. Don't forget to divide by that 3. But I think it's a better way to go about it. So what we need to do is basically solve this red integral. So it's pretty simple. I mean, something we've already done now. So we have, I think it's just x cubed minus x squared, I think, from 4 to 1. And this is a skill we have to have down. What I'm writing in red has to be something we know now. We cannot survive unless we have that. So just if you derived what's in red, would you get what's in the integral? Would you, if you derive this, you get 3x squared minus 2x. So that's the antiderivative. So we really just need 4 to the third minus 4 to the second. And then we need to subtract 1 to the third minus 1 to the second. Okay. Well, it's really just going to be, let's see, I think it's going to be 64 minus 16. 64 minus 16 minus 0. And if we take 16 from 64, I think we have 48. So that's the area of the width of the region. But do not forget about the divide by 3. We have to divide this, because technically this whole time we were dividing this by 3, right? The whole time this was here. So we can divide this by 3, and we get an answer of 16. What does it mean? Well, let's look at a graph and see if we can understand it a little bit better. So we have this parabola, and you kind of see it here. And we want to go from 1 to 4 on this parabola. So we're here. We are at 1, 2, 3, 4 here. Okay? So what does that mean? Well, it means that 16 is the average height of this function. So let's just take blue and go to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. I think it's right here. Okay. And what they're saying is that the average height of this function is 16. I want to make sure my scale is okay. I think these might be going by 2s. So give me just 1 second to figure that out. Okay, so I just regraphed. I didn't want to be wrong about that. So I believe these are going by 2s. This is a graph where this is -1, this is 6, and this is 40. So this is going by 2s. So this makes sense that this would be the way it would be. If we look at this graph, 2, 4, 6, 8, 10, 12, 14, 16, it's saying that this would be the average height of the function for those four. Okay, kind of get a general idea there. And if we look here, same idea, 2, 4, 6, 8, 10, 12, 14, 16, this would be the average height of the function. Okay. So then the question becomes, how well does the red area do at approximating the blue area, right? And our image is not really doing great. You know what? This image is still ruining things for me, I think. So I'm going to get rid of this for just a second because I know it's causing me issues. So what I want to know is how well is the blue area approximated, the blue area under the curve, right? So that'd be this. I'm trying to make it really big. Take a look at that area. Tell me what you think that is. Get an idea, okay? And then take a look at this area right here, right? Red area. Would you agree that those areas are the same? That's the question. And you can't tell, like, perfectly, but it does look like they're pretty close to accurate. So the area of that red box should really be 4 by 16. It's 48. So this red area should really be 48. It's 4 by 16. And then the area under the curve, the blue area, right? This area should equal also 48 because we integrated to get that. So what's happening is that these are getting the same area. So what we're seeing is that that 16 is the average height of this graph. Sometimes it's higher, sometimes it's lower, a lot of the times. But that's the average height of the graph. Okay, so that is the average valuable function. And we'll stop there, and then the next one will be pretty straightforward, the next example.